Yeah, hi, I'm Joe. Yeah, this is my talk today, Back to the Future, Rethinking Data Infra Scaling in Cloud, right? So I'm very glad to be here, and a little bit about myself. So my name is Joe. I work at a company called Dragonfly, and it's also a database company, so more on that later. But before Dragonfly is actually my first dev Rails role, and before that, I was doing all backend, as you can tell. And I'm actually very nervous right now because I'm totally introvert. You know, this is my first dev Rails role. So when I talk to you, I look at my shoes. That's how an introvert. You know, if I'm looking at yours, I'm extrovert already. Yeah, and my friends at PinCab encouraged me to apply for talk. I was like, okay, let's do that. And then I got it, and I was like, okay, but just until probably 1 hour ago, I realized that I'm going to be on the stage. So yeah, but anyways, I'm here. And a little bit of guilty confession that I haven't seen this movie before. So to prepare for this talk, I did it you know, a couple of days ago. So instead of preparing for the talk, I was watching that movie. Cool. So yeah, I remember that like more than one speakers today, they all have like a history section in their talk. So I was like, why is that? You know, I also have this section, but given that we're in the computer history museum, I think that fits quite well. So talking about the 90s, right? So I heard a story back in China. They're talking about the banks in China, but I kind of feel that it's global. You know, it's the same situation where the banks or financial institutions, they started to build the first generation digital experience, right? So they are very rich, and they have to have like absolute certainty in terms of their data consistency, right? So it has to be super reliable, and there's not much choice on the market by then, right? So we see IOE, you know, servers from IBM, the Oracle database, and the storage from EMC, right? So they are like the best choice by then. And they're quite stable. They're very good, and they're still very good today, right? And but you pay a price for it, right? So yeah, that's what happens. And in the 90s, and it supports like very high transaction volume, and complex query is very good as well. Then fast forward a little bit, in the 2000s, we have the young internet companies like Facebook, right? So social media, and you know, by then they're not financially strong, and they cannot pay probably the Oracle bill, and they're very innovative as well. They have like a very strong engineering team, and you know, started with the open source technologies like MySQL, Postgres, and that's where the whole internet era, open source coming, I suppose. And yeah, one thing I find very evil is the manual sharding, you know, in the application level. I just think that that's something that needs to be handled by the database itself, not by the application, right? But you know, by then we don't have much choice, so we do the sharding, and it works very well for a while. And then talking about a little bit about the hardware as well, right? So up until 2005, we have these Moore's law, basically, like the number of the transistors will double on that single chip, you know, after a period of time. But around 2005, we start to see those multi-core. I remember that the advertisement of Intel core, dual core processors, right? Everywhere on the street. And it has like 2 hyperthreads per core as well. So it's actually 4 threads. So that's the whole thing started. We cannot add more transistors, so let's add more cores. And then, you know, we have Google, like the first, probably the first and one of the most innovative hyperscaler there as well. They just decided that, yeah, we cannot do this like patch application level manual sharding anymore. Let's do it right. So they kind of like GFS is one of the very first pioneer in terms of distributed systems, right? So they have the system, and then on top of that, they have like more compute, more ways to do computation aggregation, and then to query stuff. So yeah, that's kind of like the the very first, one of the first pioneers of distributed systems. Cool, so now we're in the era of cloud computing, right? So I'm glad to be here and, cloud, scalability, AI, everything. I'm just glad to be in this era. And let's look back a little bit, the very first 5 services. Like now, if you look at the AWS console, you have 200, maybe 300 services. You're kind of wondering what do they mean? Like sometimes the names are confusing as well, right? But if you look back, the very first 5 of them, they're all about compute and storage, right? Object store, the queuing system, compute, SimpleDB, not very popular right now, but one of the first services as well, and EBS. So basically, compute, MQ, storage, right? And then on top of that, they have like these more fancy services, like AI-based and whatever. But yeah, that's kind of like the fundamental cornerstones of the whole platform. That's how I see it, right? And talking about the instances, let's look at these 2 examples. So we have this small one, AWS C7G medium. That is 1 vCPU and 2 gigs of memory, right? Then we also have that metal one, which is 64 and 128 gigs of memory, right? So what really is this, right? I wonder this, like, when I first tried to start an instance on the cloud, and I wonder what that is, right? So is that a Raspberry Pi? No, right? Because this is actually a dual core, and this is one CPU, right? So not that. What about the metal one? The metal one is kind of real. It's a super strong server. There, 64 cores. It's a huge machine, or very powerful compact rack. That's how it is. It is the hardware, as the name suggested, the metal, right? So what you actually get for the small one is a virtualization on top of that, right? That's why sometimes we call instance, sometimes we say VM. You don't really know if it's VM or it's, but for the smaller one, for sure, you know that it is virtualized. So we will discuss this more later, right? So yeah, and also people talking about microservices, distributed systems, and it seems that there's just that trend where people prefer to manage like a cluster of 32 single core Raspberry Pi servers instead of having a super powerful one to handle 1 million QPS on a single machine. That's the trend. And I kind of feel that, because of that, we have high availability, we have sharding. From a microservice perspective, it's resilient, right? So that's kind of how a developer feels right now, right? So today I'm gonna try to look back in the future and challenge this a little bit. So my take today is a little bit different, but yeah, let's keep going. And let's step back to take a look at how vertical scaling, like scale up, is doing right now, right? So I worked for IBM for 2 years, but I never see the physical machine, and I Googled it. And this is what we would have today, not today, actually, 2022, right? So this thing is called an IBM multi-frame, V16. This beast has 200 processors, and each of them is clocked at 5.2 gigs and 40 terabytes of memory. And this whole thing, it has built-in redundancy. You can run like a distributed system on that single machine because it has built-in redundancy, built-in high availability. Unless there's like an earthquake or fire or something that destroys this thing, it's pretty much resilient, right? Maybe you put TiDB on there and all your problems solved. That's, So we have hardware like this in the market. We just probably don't pay a lot of attention to that, right? So what I'm trying to say is that, yes, as your business grows, eventually one day, if you're Pinterest, LinkedIn, Airbnb, one day you're at that scale, you need to scale horizontally, but we need to keep in mind that there are drawbacks of the horizontal first strategy, right? Some of them are, for instance, wasted resources. I write backend code mostly, so I know they're stateless, but when your service starts, does it read some sort of config? Does it keep it on like memory runtime a little bit there, right? Those are duplicated, not shared across your microservices, right? So it's kind of a little bit of waste over there. So also they don't have shared memory. So each microservice instance or service that you run, it has like its own memory space and you manage stuff in there. And they need to communicate with each other a lot as well. So they're gonna compete for the network. They do RPC calls. So yeah, network is gonna be busy as well. That's why if we look back at the two instances that I just talked about, right? So the metal one, it's allocated with 30 gigs of network, whereas the single core one is allocated with up to 12.5. So if you do the math here, just multiply the 12.5 by 64, you get 800 gigs. So AWS knows that if you go with this instance and you manage like 100 of them, they know that you're gonna overuse the network. That's why they're overcommitting the network, right? That's an example. Another example is we tried to run Redis on the instances as well. On a non-busy one, when it doesn't have like noisy neighbors, you can get, that's a quite standard benchmark number there, 153K QPS, right? But because it's an in-memory data store, when there's noisy neighbor, it tends to be more sensitive, and you get like only 1/10 of the throughput, right? So with that said, because the smaller instances, they're shared, and if you do that for the 32 instances cluster you manage, you won't get the expected throughput, right? So if you want to get that throughput, you need to make sure that you are the bigger fish in that shared environment. So to get that throughput, that's not bad luck, it's bad by design. And another example is about distribution. So if we run this use case, 500K keys, 1 million QPS, with 8 shards, you can see that the data, hash functions. With 8 shards, it's kind of even, but if you add more shards in there, right, like sometimes mass just behave the way, that you cannot predict. So you're gonna have screws. And based on this experiment, we observed 20% instead of 2% for 64 shards. So that's another problem to consider. You will have like hot instances. And finally, I promise this is the hardest slide of my talk or talks of the whole day, but some math over here. If we over provision, like if we have load of L, and we over provision it a little bit by a coefficient like B times square root of L, right? So that's good, we're good. Then if we distributed this whole load to K instances, right? Each instance is gonna handle L over K, the load, right? So for each of the instances, we need to over provision, still with this factor. And then because we have K instance right now, we do the calculation, you realize that you're gonna have square root of K times, more capacity that's being over provisioned. Another way to see this is kind of like the call center example. If you have a 100 people call center, maybe you over provision it to 110, that's gonna handle your traffic. But if you have 100 individual call centers, right? There's no 1.1 person, so you need to over provision that individual call center to 2 people. That's basically what this whole thing is saying over here. Cool. So I said, some bad things about horizontal scaling, but it's not bad. It's still the gold, like the king. But I'm trying to say here today is that premature horizontal scaling should be avoided, right? So you need to make sure that your system, your software, is able to push your hardware to the limit first. And when you hit that limit, there's nothing else you can do, then probably we go with horizontal. So let's recap a little bit. So yeah, I think we should seek a balance between vertical versus horizontal, right? And as I said, software, whatever database system you're using, the software itself should be able to fully utilize your hardware. Otherwise, it's probably not considered good. And again, I don't like it personally, so probably don't do application level manual sharding. If you hit it, use TiDB. Don't shard yourself. Cool. So that's that. And yeah, as I said, I work for Dragonfly DB, so I need to talk about Dragonfly, is one of my favorite databases right now. So in the primary database domain, you have TiDB to solve your problem. What about in memory? What about caching, right? So Redis is kind of like the de facto choice in the industry, and we consider Dragonfly as part of the Redis ecosystem as well. We all love Redis, but it's famous for its single thread. It's actually not single thread. Like it has multi-threading to do other stuff, but for the data manipulation, for the core functionality, read, write, in-memory data of Redis, that's still single-threaded, right? Because of that, a single Redis instance is not able to utilize your 64-core machine. That's just the fact. In order to do that, you need to run a clustered Redis on that single machine, right? If you think about it. So that's why, we team at Dragonfly, we build a multi-threaded, shared nothing, Redis compatible in-memory database. So it's not a fork. It's built from scratch, just kind of like the relationship between TiDB and MySQL. It's compatible, but they don't use the same code. And we believe that if you have like a single binary of Dragonfly on that powerful machine, you don't need to manage a complex cluster, right? That's how we try to. There are other problems Dragonfly tries to tackle to solve the pain points of Redis, like snapshotting as well. But overall, we want that single piece of binary being able to utilize your computer, your hardware resources, right? So there's some like introduction here. Yeah, so Dragonfly scales vertically first. And we were able to do 4 million QPS on a big-ish AWS machine. And we also solved the problem of snapshotting where, because in Redis, you use the system fork, which is copy on write. So if your Redis instance is busy with writes as well, your memory could double in the worst case scenario, right? Dragonfly use a multi-version, lightweight, and algorithm to solve this problem. So when you do snapshotting, while heavily hitting the instance, you won't have like spiky memories. Yeah, so that's what we're doing right now, and it's source available on GitHub. So yeah, if you're interested, remember to check. Last but not least, I want to show you something. Let's look back in the history, look back in the future again. So how many of you know what this project does? Codis. Very awesome. Yeah, Ed knows. So the co-founders of PingCap, Ed and Max, before PingCap, this was one of their projects. It's a Redis cluster solution. So it's before the official Redis cluster, right? So it's kind of like the pioneer before the official Redis cluster, right? So in Redis cluster, each instance keeps a copy of the cluster information, and they use the gossip protocol to exchange that information, which is well designed in terms of like all the nodes does the same thing, right? But if you have like a very large scale cluster, then all the instances in Redis cluster, they are just busy exchanging the cluster information instead of handling your data request. Codis uses a different approach. You can see the TiDB architecture, vibe in there already. So it has like a centralized dashboard and it's proxy-based, right? So Dragonfly also looked back in the history, and Dragonfly also, I cannot click this anymore. Sorry about that. Cool. Next slide, please. Yeah, so Dragonfly also learned from Codis that we have a control plane, and for in-memory data stores, we prefer performance over, sometimes it's okay that it's not as consistent, right? So we don't have like a consensus layer in between, but the architecture is there. So yeah, Dragonfly, one instance, we can handle up to 1 terabyte of in-memory. If you go with, if that's not enough for you, if you go with the cluster, theoretically, we haven't tried, but theoretically, you can have like a 1 petabyte in-memory data store. And yeah, that's it. That's about it. Cool. So my last slide. Thank you very much. And yeah, thank you so much.